All right. Everybody ready for day 2 of Philly ETE? Yeah, I love this conference and really excited to be here. So my name is John Moore. I work on software architecture at Comcast, and I'm here today to tell you about a distributed system library we developed there called Sirius that we use for managing reference data. So I'm going to tell you a little bit about what we use it for and how it works today. So I should probably start with a definition of what I mean by reference data. Right? And so I've got a, does anybody actually recognize this picture anymore? It's sort of a good question, right? But this is the Encyclopedia Britannica, and it's a really good metaphor for the kind of reference data that we're talking about. So the idea here is this is a data set that I need to access very frequently and with low latency, but which my application is not really in charge of it, right? So my application needs to consume it on a read-only basis and may be interested in updates to it, but I'm not in charge of editing it, right? So, and the vast majority of us, for example, read things on Wikipedia and are not one of the 30,000 or so editors that Joel mentioned in his keynote yesterday, right? So the idea is this is a pretty common use case, right, where the data comes from somewhere else. In addition, just like an encyclopedia, the idea here is you're interested in updates, but the vast majority of things don't really get updated that often, right? It's a relatively static, relatively slowly changing application, or data set, but it's one where you are interested in getting the updates over there. And so that's what we're talking about in terms of reference data here. At Comcast, one of the biggest such reference data sets that we have for a lot of our applications is all of the TV and movie data that we use to drive our TV guide and web and mobile applications, right? So that was sort of the motivating use case for us. So, all right, so let's look at an example of one of these sorts of things. And so these end up having some interesting properties. So let's look at the number of feature films that are kind of out there over time. So I pulled some of this data from IMDb, right? So that's a good example of a reference data set, right, is IMDb. So in 1998, there were about 193,000 feature films that had been released as of 1998. By 2013, 15 years later, there were about 273,000. Okay, and so that's a 40% growth rate over 15 years, right? It's like, okay, that's a sizable amount of growth. Now we all know Hollywood's cheating because they're just remaking old movies at this point, right? But there's some growth, but still it's over a 15-year time period. So now let's look at a different graph. So let's look at how much RAM is available in a commodity server over that same time period. So back in 1998, you could get a Sun Ultra 2 with a whopping 256 megabytes of memory, right? And I remember that, like that really was whopping back in the time, right? So now, 15 years later, I can spin up an M3 2X large in EC2 that has 30 gigabytes of RAM. Okay, this growth rate is 12,000% over 15 years. And so if I actually take these two graphs and I normalize them and overlay them, this is what it looks like, right? So we've got the memory graph is this blue diagonal line, and that the movie graph, right, which used to look like it had an upward slope, is essentially flat. It's not actually, it's maybe 1 pixel higher over there, but it's essentially flat. And the lesson here is that thanks to Moore's law, the amount of memory that we have in our common application servers is growing much faster than a number of really interesting reference data sets. And so this is going to be something where, this is something we discovered, right, where just a few years ago it wasn't practical for us to use that reference data set that I talked about of this entertainment metadata. It wasn't practical to fit it into memory, but now all of a sudden it is. Things are growing that fast in terms of available memory. So, you may say, well, okay, that sounds good, and but you may not have sort of an idea of, well, how much data is TV and movie stuff. So let's put this in the context of some things you might be have a little more idea of. So back to our Encyclopedia Britannica, right? Which I think we have a concept like that's a good amount of information, right? So if you get it on DVDs, this is 4.2 gigabytes, right? This fits on my smartphone now. So, you know, that's not that big. So, well, let's shoot for something bigger. Inspired a little bit from Joel. So let's go download all of the English Wikipedia articles in XML format and see how big that is, right? And so, you know, XML is not necessarily noted for its lack of verbosity, right? So this is not the most concise representation of this stuff. And this is uncompressed, right? So we're going to uncompress it. That whole amount of data is 43 gigabytes, right? So that's definitely bigger, but you know, today I can go spin up you know, instances on EC2 that have 6 times this RAM, right? So even that huge of a data set can fit in memory now. Okay, so this is kind of the setting and the lesson that we had. So the point here is that there are a lot of things that fit into this reference data category that I'm talking about here that maybe you might have previously thought about. So how do we used to get access to this stuff, right? So I have my application server. This is where I want to ship my features to. And okay, well, I've got this reference data. Where shall I put the reference data? Maybe I should put it in a database. And you know, and that's what we did, right? So and we would go ahead and query it. And so, you know, all right, that worked okay. But you know, I kind of want access to this data in, you know, familiar data structures, right? Maps and sets and arrays, linked lists, objects, things like that. And well, that's not how it's stored in my relational database, right? And even, you know, even if it's a NoSQL database, right? It's like, you know, well, that tends to store things in more document-oriented sort of fashion, right? So it's still, there's a translation that has to go on here, right? So I'm like, well, that's not super convenient. I know, I'll use an ORM. And great, this will take care of this mapping for me. And that'll work out okay. But then you discover, well, gee, I kind of care about latency still. And I kind of need to really care about performance here. And so what you discover is that ORM does not expand into object relational mapping, but actually expands into obscuring the real mechanism, as anybody who has tried to tune Hibernate queries can attest. And so, you know, so this is a struggle, right? And even if we took it out and we, you know, went back to just, you know, look, I know what I'm doing, let me just write the queries. As an application developer, you know, and particularly if you saw Jeff Hodges' talk yesterday about distributed systems in production, right? One of the things that you have here, this is a distributed system, right? There's 2 communicating pieces here. And so I have to spend a lot of time worrying about things like I/O exceptions that are caused by drop connections or connection timeouts. If there's a caching layer here, I have to worry about managing cache misses and caring about the latency when that happens. You know, particularly things like the Hibernate query cache, right, which is a relatively complex cache. It's really hard to manage that and get the consistency that you want there, to the point where there are blog posts that say, you know, query cache considered harmful. You know, I have to worry about connection pools, right? And well, how many connections do I have in a connection pool? Is there a stale check? What does the stale check look like? What is the idle timeout, right? What is the overall pool size? I have to worry about all of these details just to get something that's running robustly. And none of this has anything to do with the data that I want to use or shipping features. So, you know, this is what led us to say, well, look, maybe there's a better way, right? So what's the model that we really want, right? So, okay, I've got my application server. As we just saw, it's got a ton of RAM available. And so what do I want, right? It's like, well, I want my reference data right there, right? In memory, in native data structures, you know, in the way that I want to access it, right? So this is what we decided to shoot for, right? So we said, hey, you know what? This reference data set, it fits in memory now. Let's figure out how to make that happen. So I'm going to walk you through now and sort of construct some of Sirius's features by kind of progressively enhancing this. So, and the reason that we want to do this, right, is that we want to spend our time thinking about data structures and algorithms. We want to be able to write simple unit tests to know that we did it correctly. As Jeff mentioned yesterday in his talk, profilers aren't really super useful if you have an IO-bound application. But as he said, if you can turn everything into a local problem, like, you basically won, right? And so when we're looking at accessing this data, it's like, well, hey, like, profilers, like, remember those? Like, this is a good technology. And if you're talking about things that are, algorithmic in nature, this can be a really useful tool. So, so you can spend more time working with the actual data that you need to ship your features. Okay, so first question is, well, how do we get the data in there, right? And so the first thing that we did was we inverted the usual model, right? So normally we were querying some external source of data, right? And there is an external system of record, right? Remember, that's what makes this reference data rather than application data. And so we inverted that, and instead we said, okay, let's do this. We're gonna publish the reference data into our application server. And this brings a few advantages, right? So one of them is, as the updates come in, we can just very simply in the application server say, here's an update. Let me update my data structures, right? It's very easy to maintain this data structure in this fashion. But the other thing is that it decouples the availability of the system from the system of origin, right? So the idea is that if whatever's doing the publishing goes down, right, you still have the full mirror of data, right? Maybe it starts to get a little stale, but a lot of these reference data sets, you find that you have a pretty good tolerance for propagation latency, right? As long as the updates get there, it's like they don't have to get there within milliseconds of an update happen, right? In many cases, your window may be minutes or hours, right? That's a lot easier to kind of sneak things in on. And so you can tolerate a little bit of staleness every once in a while. So, okay, so that seems like a good sort of approach. All right, well, what next? Well, we're probably gonna need more than one server. So, I'm gonna have to figure out how do I do this across a cluster of servers? And so, well, it seems like we wanna do something like, when updates get published in, maybe we can replicate those updates to the other cluster members, right? So then they can update their versions of the memory as the data set as well. Right, because basically this is such a common data set that all the application servers need the data set anyway, right? So that they can all take advantage of this locality. Okay, so we need something that can replicate things. Now the other thing that we are going to want is we're going to want to ensure eventual consistency, right? Which is that as these updates are kind of flying around in the cluster, we want each cluster member's picture of what that data set looks like to eventually converge, right? So like if I stop putting updates in, eventually they would all have the exact same data set, right? And that's an important property because if you find yourself running a distributed system in production where these things don't agree because they diverged, because there's some non-determinism in here, and it causes a problem, and somebody says, how does it get that way? How did it get that way? Your best answer is kind of, I don't know, right? So it leads to kind of operational sanity if we can ensure eventual consistency. So one of the ways of doing that is to ensure that if all of the nodes get all of the updates and they apply them in the same order, then that's a way to guarantee eventual consistency if the updates are not time sensitive. And so we looked for, hey, what's a mechanism that we have that can help us replicate these updates in a way that will allow us to have this consistent ordering. And so, we said, well, what are all the cool kids doing, right? And so they all use Paxos. And so if you're not familiar with Paxos, at a high level, this is, it's a distributed consensus protocol, right? But basically it's a way for a cluster of servers to agree on something, is really all it boils down to. So Camille Fournier mentioned this in her Zookeeper talk yesterday. And I'll talk a little bit more about Paxos later. But this is going to allow us to basically assign a unique and consistent sequence number to all of the updates that are coming in, right? And so once we have sequential sequence numbers, then we know if I'm missing any updates, and we know what order to apply them in, right? And so everybody can do that, and that's how we get our eventual consistency. So, okay, great. So the other thing that running Paxos gives us is, so Paxos is a peer-to-peer protocol, right? So there aren't any special permanent leader nodes that are involved here. So what we can do is we can actually stick a load balancer in front of these, and we can have the external system publishing in through the load balancer, right? So the update can actually go to any one of the cluster members, and they can run Paxos between them and still come out with a globally consistent ordering to all the updates. And so this is really useful because, again, there's an operational decoupling that happens, right? Because the systems that's publishing the updates doesn't need to know how many servers you have and which ones are currently up or down, right? Load balancers are really great for that, of like, hey, you're like kind of dead, so maybe I won't send you any more updates, right? So we could lose one of the app servers and still be taking updates in while we're going. And this is commonly useful for deployments, for example, right? Deployments are just intentional failures, as you restart things. Okay, great. So we've got a mechanism for publishing these updates and sort of synchronizing them around. All right, well, that's cool. But what if somebody comes in and pulls the plug on the data center? Right, power goes down, right? It's like, oh, all of these copies of the data set are gone, right? They were sitting in volatile memory. And again, we want to make sure that we're not dependent on this external system being up in order to recover from this. So, we applied, stand on the shoulders of giants, right? So we do what databases do, right? So as the updates come in, we're going to write them to a local transaction log, right? And so, and this is our recovery mechanism. So now, if one of my application servers goes down, when it comes back up, it comes up kind of with an empty brain, right? It's like, all my stuff was in memory, and I came up fresh, and I have no data, right? And so what we can do with the transaction log is we can just replay all those updates back into the system and rebuild the data set. Now, because I might have been out of the loop for a little while, because the deployment took a little time, or it took time for somebody to come back in and restart after a failure, we also need a way to catch up for anything that was missing, right? So I may come up and I have in my local log updates 1 through 100, right? But while I was out, more stuff was going on, right? That was the point of sending the updates through the load balancer, right? Was to continue processing the updates. So what I can do is I can ask my buddy and say, hey, do you have like 101 through 150? And my buddy can say, sure, here you go, right? And so I can actually find the missing updates and then add them to my transaction log, right? And so this addresses both a server that's been out of the loop for a while, but it also addresses just simple lost messages, right? So this is also a way to recover from partitions, right? If you were on the minority side of a network partition, and the majority side was processing updates, once you reestablish connectivity, this lets you catch back up and find out what you missed, right? So this is a really sort of useful operational property, right? This catch-up protocol means that we don't have to do a lot of operational interventions in order to recover from these types of failures. And the other thing this lets us do is if we want to deploy a new instance, right, a brand new instance, right, which is like, again, has an empty brain, but it doesn't even have any transaction log. Actually, the same mechanism can be used to completely bootstrap that new instance if you want to. We have done this sometimes, but sometimes what we do is like we actually just SCP the transaction log over to the new server and then start it up with something new, because sometimes that's faster than doing this. So, but again, it's, there's operational flexibility here, right? Which is, operations folks like to have operational flexibility, and so that was what we were shooting for here. So, all right, so we're publishing things in through the load balancer, and this catch-up protocol actually lets us set up something more interesting, which is that we can have really flexible replication topologies. So, I can be publishing my updates up in here and processing those, but I can also have dependent clusters set up. And the idea here is these 3 clusters could all share actually the same configuration. So with Sirius, it's a pretty simple static configuration file, right, which says, here are the cluster members. And then it's basically, when the server comes up, it says, am I in the list? If I'm in the list, then I'm going to participate in Paxos and process updates and vote on stuff and things like that. But if I'm not, then I kind of go into passive mode, and all I do is just play catch up, right? And so what I do is periodically I'm going to wake up, right? I'm going to say, what's the last number update that I had, right? Oh, it was 300, right? So periodically I'm going to wake up, I'm going to pick one of the primary cluster members at random, and I'm going to say, hey, do you have the next n updates after 300, right? Do you have 301 through 325, something like that? And then the catch-up protocol will come back, and if I get a full window, right? If I actually get 25 when I ask for 25, then I say like, oh, I must be like relatively behind here. So then I'll just immediately keep trying to stream the updates until I get a partial window. Right? If I get less than what I asked for, then it's like, aha, I'm like relatively caught up now, and then I'll go to sleep for some period of time. So you can actually use this, and we do, depending on how you configure the sort of polling frequency and the size of the window, and this depends to some degree on the rate of updates to your reference data set. You can actually stay within a couple seconds pretty easily, even across a wide area network. And so this works out pretty well for us. And this is how we replicate the data across between data centers, for example. The other thing that this lets us do is it lets us separate some scaling concerns, right? So in particular, we can divide responsibilities between two types of functions that kind of have some tensions on cluster size. So on the one hand, if I want to process as many Paxos updates as possible, it turns out smaller cluster sizes are better, right? The more people you have voting, the slower the Paxos throughput is. And so that says, well, if I want to process a lot of updates, I want a small cluster. But on the other hand, it's like I want to serve a lot of clients, so I want to have a big cluster. And so this is a well-known, scaling pattern, right? Like we do this all the time with traditional database replication, right? Which is like you have your write master and then your read slaves, right? And you can scale a read side out as far as you like, right? And so this works out pretty well. Okay, and so overall, that's sort of the set of functionality you get using the Sirius library. So I'm going to dive a little bit more about what does it look like when you use it, right? How do you from an application developer's point of view, what does it look like? So Sirius is implemented in Scala, and so it runs on the JVM. The sort of official interface to it is actually just a plain Java interface, though, and so you don't have to know Scala. Per the keynote here, like you don't have to be scared of the library. It'll work. But the interface that it exposes is relatively simple. There's essentially really two major functions that are in there. The actual interface has a couple more, but for the purposes of what do you want to do with it, there's really only two, right? So the two things that you can do, or one of the things you can do is you can say, hey, Sirius, I'd like to do a put, right? So I'd like to, this is a key value interface, right? I'd like to use this arbitrary byte array as the value to be associated with this key, which is a string, right? And if you'll note, what you get back is a future, right? So this is asynchronous, right? You can just say like, I would like this put to happen at some point. And then similarly, you can enqueue a delete, right? Which says, I no longer want any data associated with this key, right? So that's all it is. It's a key value interface, but it's very general, but that's all there is to it, right? On the flip side, in order to use this, you also, as an application developer, have to implement an interface, right? So there's a corresponding request handler interface, which Sirius will call back in with these updates at the appropriate time, right? And there's basically two methods here, right? Which are handle put and handle delete, right? In terms of updates. And you can see there's a pretty clear correspondence, right? And so what ends up happening is that your application kind of gets divided into two layers, with Sirius playing an intermediary role. And so let me walk you through sort of through the update path here, right? So remember, we've got this external system that's publishing the updates in. And so an update arrives at your application, and by whatever its native interface is, right? For us, a lot of times this is an HTTP web service, right? So we just have some other endpoints for receiving the updates as they come in. But there are other options too. Other groups have other mechanisms for getting the updates and sending them through Sirius. And so what I do is I say, aha, here's my update. Sirius, please, I get to decide how to represent that in terms of keys and values, right? And so I can say to Sirius, okay, please, let's handle this put or this delete. And so then the Sirius library layer, right, does the Paxos stuff, right? You don't have to do that part. It takes care of the catch-up protocol and things like that, right? So we're assigning sequence numbers, we're writing things to disk, and managing things that way. And at the appropriate time, right, because remember, we're shooting for eventual consistency, right, which means that it's important that we apply the updates in order, right? So if I've got update 100 and 102, right, I can't apply 102 till I've gotten 101, right? I want to get all of the updates, right? So Sirius may need to wait until it's found update 101 from somewhere if it's missing it, right, before it's time to feed it in, right? And so when at the appropriate time, then it issues the callback, right, to that request handler, right? And so then this is the point where you update your native data structure. And so it's, one of the things you can imagine is kind of a null Sirius layer, right? Which is when you say enqueue put or enqueue delete, it actually just turns around and calls your callback. Like you could imagine that. And so it's easy to understand how the data flows through your application that way. And so what this means is you're in total control of the data structures that are used down here and how and when they get updated, right? Sirius will tell you, hey, here's the next update to apply, right? And it does them one at a time in a synchronous fashion. So it's relatively easy to keep things updated this way. On the read path, things actually get even easier, right? So we don't actually have to go through Sirius on the read path, right? So if I actually get an API request or a client request where, okay, now I want to use the data, that like the whole point, this is the whole point, right? The whole point of setting this up was to make this part easy. Right, and so what's involved here? It's like I read the data structures, right? I mean, this was the point, right? The point is this path is easy. Now I'm using native data structures. This is the very first type of programming we all learned when we learned how to programming, right? It's like maybe there's I/O, which is a printf, but everything else is just data structures in your program. Like that's what we're shooting for, right? It's that convenient. In terms of getting access to this stuff. All right, so that's the overall concept, right, and what it's like to develop with it. So there's one more operational detail that I want to mention here because I didn't want to mention it till I'd had a chance to introduce this idea of the puts and the deletes, right? So one of the things astute folks in the audience may have sort of realized that, well, hey, you got this like transaction log hang over there, and it's accumulating updates right as they come in. It's not going to get big, and so the answer is yes, but this is where the key value interface actually comes into play, right? So what's in the transaction log, right? So the transaction log is just a collection of updates, right? So it has things that say like, hey, assign this value to key X. Right, it's that's what a put looks like deletes are similar, right? And so it's going to accumulate these updates over time as they come in, right, according to various things. Now, because a put is an idempotent operation, right, and it's a complete operation, right, it's a complete replacement. What that means is, remember, the reason we have the transaction log is just to support replay, right? So what we do is let's look at variable X, right? So we've got two updates in here that talk about X, right? But if what we want to do is get to the eventual final state for X, I don't need the old one, right? I just need the most recent one, right? So I don't need that earlier one, right? And similarly, in this example here, I can get rid of the older mention of Y. And what this lets me do is that we can compact the transaction log, right? Because all I need is the most recent mention of any of the keys. And Sirius can do this without really understanding the semantics of your data, right? Because it's not looking at the values, right? Those are arbitrary byte arrays that you defined what they were. All it needs to know is like, what was the name of the key and is it a put or a delete, and the appropriate sequence numbers to keep things in order. So Sirius can take care of this stuff without understanding what your application's data is or what it's doing with it. And this is really just due to the fact that this was the key value interface that we saw before. So, so what that means is that over time we can do these compaction operations, and the size of the log on disk stays about the size of the reference data set, right? Because that's all that's in there, right? It's the most recent values of things. You know, as we saw before, right, with the graph with, you know, memory looking like this and like the movies looking flat, these reference data sets really don't grow that quickly, relatively speaking. Right? And so the overall data set size tends to be relatively static. Yeah, there are updates you have to apply, but the overall size stays relatively constant. And again, we're looking at things that are in memory, right? So it's not, you know, if it fits in memory, like you probably have enough room for it on disk too. And so the main thing here is, one of the main motivations for compaction actually is just to speed up replay, right? You know, there's no sense in replaying that first update to X because I'm just going to throw it away later. Right, so you can do things in this fashion. All right, and so what we used to do here was when we would do this compaction step offline while the application was down. So we would actually do it during deployment. So the first service that we were developing that was powered by Sirius was doing a lot of continuous delivery. So there were relatively frequent code updates that were going on. And so what would happen is, you know, you knock. You know, we're doing rolling restarts, right? So I knock one of the application servers over the head. I compact its transaction log, and then I start up the new code version, right, with an empty brain, and then I replay the compacted log. And so that's what we would do, right? And so, you know, repeat for all the servers. And that worked, but we sort of had that. It kind of bothered us a little bit. Right, in the back of our heads, right? Because on the one hand, we were relying on the fact that we were deploying this thing all the time, right? So we had easy, convenient opportunities to do this compaction. And you know, you don't really want to ask your operations folk to go messing with production if you're not really updating anything, right? Like you don't want to schedule downtime for these things just to do maintenance work, right? And so that bothered us a little bit because, you know, we thought, well, eventually the service may not be as frequently or developed, right? We may not do these frequent deployments. But then the second thing was having this compaction step in the middle of the deployment process just made the deployment process take longer, right? Because the compaction step could take, you know, several minutes to do that. And so that's several minutes per instance that you're adding up in terms of doing a whole deployment, right? So that was also kind of inconvenient. So we later figured out how to kind of take care of this in the background. And so Sirius will do this in the background. So what we do is instead of a single transaction log, we actually break things up into segments, right? So Sirius will start logging things to a transaction log. And when the segment reaches a maximum size, it stops writing to it, right? And it starts a new segment. And when that one hits a maximum size, then, you know, it starts writing to the next one, right? So the segments have a maximum number of updates in them. And what that lets us do is, while we're writing to a later segment, we can actually in the background go ahead and compact one of the older segments, right? And we just do the same compaction algorithm that I showed you before. We just do it just on that segment, right? Now what's left there, right? You know, there could still be, you know, an X up in that top segment, and then, you know, we may have done some writing down here, right? So it could be that we still have some outdated data up there, but it's okay, right? We can still compact some things that may have actually just been mentioned just within that segment. And similarly, we can just keep doing this, right? So we can go ahead and compact the next older segment, but when we do that, we compact it and all the older segments at the same time, right? So when we're compacting this one, we can also potentially shrink the older ones as well, right? So over time, this ends up adding up where you can really keep up in the background with this stuff. And you know, Sirius is good about, you know, if it crashes in the middle, you know, it doesn't get confused about where it was in the compaction step. It really just kind of says, whoa, there's some like intermediate compaction thing that looks like it was going on, so I'm just gonna like kill that stuff and start over from, you know, from scratch for whatever segment I was on. So that works out a lot better. And so what this means is that Sirius will do the management for you, right? So you don't have to do a deploy offline compaction anymore and can do it online. The reason we had to have a maximum segment size is that to do the compaction efficiently, you end up wanting to build an in-memory index of sort of which updates for keys are in various places. And so we want to cap the segment size so that that index fits comfortably in memory without causing problems for the application. Right? And that, the size is a tunable parameter. Okay, so, so I think at that point, this is really all the main functionality that you get with Sirius. So I want to talk a little bit more about implementation. So as I mentioned, Sirius is implemented in Scala. And we actually heavily use the ACA actor system. So if you're not familiar with actor systems, this is sort of the main programming model that you see in languages like Erlang, for example, is a good example of a language that uses it. Basically, you have little finite state machines that send and receive messages. And so this ended up being very convenient for us. So I mentioned the Paxos protocol before, right? So Paxos is a notoriously hard to understand protocol. And so it was invented by Leslie Lamport, right, who just won the Turing Award. And in fact, when he first wrote the paper about Paxos, he couldn't actually get it published because people kind of didn't understand it and they didn't understand what it was useful for. So years later, he wrote another version of the paper called Paxos Made Simple. He's like, I need to explain this more simply so that people get what this is. It's simple if you're a future Turing Award winner, right? This is not a simple paper. And so what we did was we found a great paper by Robert Van Rennes called Paxos Made Moderately Complex, which is really a tongue-in-cheek reference to this Paxos Made Simple. But it's a much more accessible paper. And so it has pseudocode in it that describe the various processes that go on during Paxos. I apologize for the small font here, but this is a snapshot of one of a snippet of the pseudocode from the paper. On the right-hand side, I have the current Scala source code for that same process from the Sirius codebase. And if you look through it, there's a pretty straightforward one-to-one correspondence here. There's not much that appears on the right-hand side that isn't over here, right? Okay, there's a try-catch. We've got to do some, academics never handle errors. But there are some other things that are in here, right? We did have to implement some of the optimizations, for example, that are mentioned in Google has a paper called Paxos Made Live, which talks about their Chubby implementation, where they talked about some of the implementations, improvements that they had to do in order to sort of make things practical. So there's a few other stuff in here, but in general, it was a pretty clear one-to-one correspondence. And for folks who are trying to figure out how the Paxos protocol works, at the same time that we're trying to actually implement it and have it work, the fact that there was such a small gap between what we were trying to understand and what we were trying to implement was a huge win. Big ups for ACA there. The other thing we did was we wanted to evaluate sort of how good this Paxos implementation was, because we didn't actually spend a lot of time optimizing it, right, to get the maximum throughput possible on it. As I mentioned before, right, we have these reference data sets and they don't have crazy update rates, right? Like updates happen and you care about them, but it's not massive throughput because the whole data set is not that big to begin with, and not very much of it is being updated over time, right? It's like an encyclopedia. But we still were curious about how good this was, and then we also wanted to see how easy it was to use Sirius. So around the time we had a new team member join, we decided, okay, let's take something that we know is battle hardened and see how Sirius stacks up against it. So we took Zookeeper, right, which we use to good effect in other parts of Comcast. If you saw Camille's talk yesterday about Zookeeper, she had a really clear explanation about what the good use cases are. But this is a battle-hardened piece of software, right? This is tried and true, and it doesn't have a Paxos implementation in it. It has a protocol called ZAB, or Zookeeper Atomic Broadcast. It's also a distributed consensus protocol, so it's doing the same kind of thing. And so what we did though is we took Zookeeper and we ripped out its persistence and ZAB layers, and we plugged Sirius in instead. And then once we did that, we were able to run an external third-party benchmark against the two versions. And so I'm going to do something weird now, and I'm going to show a graph where our stuff is slower than the other guy's stuff, which I know is sort of rare honesty, so let me explain what this graph is. So up here on the y-axis, we have the different operations that went on during the benchmark. You don't really have to understand what this is. The first four are updates, and then the bottom one are reads. And the dark bars here that's native Zookeeper. And the light bars are the Zookeeper Sirius Frankenstein thing that we put together. And as you can see, and sorry, we have throughput over here on the x-axis, right? So longer bars are sort of greater throughput. And so, as you can see, like, oh, well, the native Zookeeper goes faster. So I want to be clear, though, about what we were trying to do when we did this benchmark, right? It wasn't go build a better Zookeeper, right? Zookeeper is awesome at what it does, right? Zookeeper is already a pretty good Zookeeper. And so instead, we wanted to kind of really look at two things. Like one is our Paxos implementation in the ballpark, right? Which is like, okay, it's a factor of 2 off, but since we didn't spend a lot of time really trying to optimize the performance here, like that was okay. And again, that throughput wasn't, isn't super critical, right? Well, like we don't need tons and tons of throughput. Like more would be better, certainly, but we got enough for what we were trying to do. Of course, on the read side, right, Zookeeper Series is just reading out of local memory, right? As is sort of the regular Zookeeper. So that's what you want, right? Except you get to read out of native data structures and trying to figure out how to navigate nodes through Zookeeper. The other thing we wanted to evaluate was how hard is it to use Sirius? So as I mentioned, we had a new team member join, right, who was familiar neither with Zookeeper nor with Sirius. And so it took him more than a day to get this working, but it didn't take him months, right? It took him a couple of weeks, which I think for somebody not familiar with that code base was a pretty good validation that it was relatively easy to use Sirius once you figured out what Zookeeper was doing. So, all right, so about time to wrap up before we get some questions. So we've been running Sirius-based applications in production since August of 2012, right? So in a few more months, we'll be at the 2-year mark. So we've certainly found our share of bugs here, right? It was certainly not bug-free from the first time we used it, but as you may have gathered from my description of some of the features, we try to engineer this to be a really operationally friendly system, right? That when there are failure modes, it's like a safety elevator, right? When your cable snaps, you fall 6 inches and you stop, right? So for a lot of this stuff, if the updates stopped happening because we had a bug in Paxos and it got stuck, well, that's okay because the read path didn't go through Sirius, right? So from the application point of view, we didn't lose availability for the applications, and so that was pretty good. That was really good. And so at this point now, we actually have multiple products and services that are powered by Sirius-enabled applications, including our X2 interface, right? So this is our new user interface, which is currently in market trial. Lets you watch TV on your iPad in your home, right? It's the same as the TV connected to your set-top box. And so a number of the APIs that power this service and others are using Sirius under the covers to get access to their reference data. And so we really like it, right? We keep running into more teams within Comcast, right? And I don't have very many people that report to me at Comcast, so like I can't make people use it, which is actually, I think this is actually a good thing because people are opting into it because they find it useful. And the reason is that Sirius provides access to your reference data with a number of really important properties, right? So the first one is, from an application developer point of view, I get to use native arbitrary data structures that I control that are suitable to the use case that I have for my data. If I need a doubly linked, crazy linked list circular data structure because that's the appropriate data structure, I can have one, right? There are lots of products that have, I call them magic hash tables, right? Which is like, as long as you can put things in the hash table, like the hash table will magically replicate it sort of everywhere, right? It's like, well, and actually that's real, so don't get me wrong, like that's a very common and useful use case, right? But we did and we have found situations where we actually did need custom data structures to get the kind of performance that we wanted in accessing this reference data set. So this fact that it's these native arbitrary data structures was really important. as I mentioned, getting the eventually consistent replication is good for operational sanity. Sirius also takes care of the persistence and replay, right, which is a big part of decoupling ourselves from the availability of the reference data system, right, the system of record for the reference data, right? If we have a failure, the last thing, and multiple failures going on, it's nice to be able to recover things, without dependencies. And then finally, there's a really convenient and understandable library interface, right? As we saw, right, it's this, enqueue put, enqueue delete, and then, I get a handle put, handle delete, right? And I basically get back what I put in, I just get it back at the right time, right? And I get it back on all of my nodes. So that makes it pretty straightforward to use. And so we're really happy with it. And so as my T-shirt sort of hints here, so this was developed here in Philadelphia. And so I'm really happy that at Philadelphia's premier tech conference, I'm really happy to announce that Sirius is also available as an open source project on our GitHub page. And so, there's a lot of work that went into this. We're really proud of it, and we're really happy to give back to the open source community in this way. So at this point, I'd be really happy to take any questions anyone might have. So I think we got microphone kind of running around, or.
So how does this compare as far as use cases go with data grids or distributed caching?
Yeah. So one of the big deals with distributed caching is that in some ways I think it's complementary. So one of the things that we have here is that the data set that we get in memory is not a cache, right? Really, a mirror is probably a better word for it. So caches imply that there are things like cache misses, right? And where I tend to have a hot subset of data here, whereas here we're getting a full in-memory mirror. But what we actually find is that this meshes really well with other technologies, right? So it turns out this reference data is so ubiquitous, we actually need a copy of it everywhere, right? We shard on other things, right? So we have various personalized data that we're going and pulling in from various distributed and sharded data stores, and that's a more traditional path there. But then we tend to mix this reference data in, right? So we really need this data everywhere, and so that's one of the differences here. The other thing is on the read path, right? That there's nothing in the way of the read path there. Right? There's no magic that's going on there. It's my data is there, and I just read it right out of the data structure. So there's sort of it's easy to understand what's going on that side.
I did have one other quick question, but
I
think you just answered it. So there's no way to set this up partitioned as opposed to replicated?
Not currently, yeah. So again, the idea here is that this takes care of the single data set where you actually need the whole data set everywhere. Because the data set is small, right? And again, currently this is targeted at, the reference data set is small enough and important enough that it matches this use case, right? I actually need a full copy of it at all the application servers because it's that ubiquitous of access. Yeah? Oh, you're closer to the microphone, but we'll come back to you in the back there in a second.
Yeah, from an application developer's standpoint, your interfaces should byte arrays. Can you comment on the pains of serialization and any pro tips on that if I'm going to implement Sirius?
Yeah, so the nice thing there is, so I have a couple things to say, right? So if you're in the keynote about Java, right, one of the pain points they mentioned was serialization, right? Sirius is serialization agnostic. That's hard to say. So you get to decide how you want to do that and what library you want to use. But the other thing to realize is that really only happens on the write path, right? So it's when the updates come in that you turn things into the byte arrays. The byte arrays are what gets stored in the transaction log, right? You kind of need it because you have to transmit these things across the network and to disk. And generally speaking, I've found that a lot of application developers like to be in control of the serialization that's going on. we need it to be serialized. So we just present that interface, right? Because it's pretty transparent and the most flexible sort of thing. But again, once it comes back, right, in the request handler, when Sirius actually hands it back to you, okay, yeah, you convert it to whatever you want, but then you store it in non-serialized data, right? So on the read path, which is the common path that you care about, like there's no serialization going on in there if you don't want there to be. Okay, back.
Can you talk a little about how you handle cluster membership?
Yep. So currently cluster membership is just a static configuration file that says here are the members of the cluster. This was one of the simplest thing that could possibly work kind of approaches here. So Sirius does look for changes there, right? So if you change the configuration file, it will say, oh, I see that you don't have to restart it, for example. But that's actually, that configuration file is what lets us set up these flexible topologies. And you can actually have chain topologies, right? So you can imagine I have cluster A, right? And they have the same configuration file, right? Which lists all of the members of cluster A, right? So they all wake up and they say, aha, I'm in that list. We're going to do Paxos, right? And then I can come over here and I have cluster B, right? And they actually have the same configuration files, right? They list all of the servers in cluster A over here, but they all say, oh, I'm not in the cluster. I'm just going to play catch up, right? But now I can have cluster C over here, and their configuration files can actually list the members of B. Even though B aren't participating in Paxos, the catch-up protocol doesn't care. It's like, I'm not in there, so I'm not doing Paxos. And so I'm just catching up from these other folks, right? And because of the eventual consistency, like the updates can actually propagate this way. You can do fancier stuff too. Like you can actually list, and we do this, because we're running across multiple data centers. So you can actually have, depend on all of the servers in different data centers, right? And so when you wake up, you're going to pick one of them at random, and so you'll pull from this one or you'll pull from this one, just depending on how things go. But it means if you lose your connectivity to this data center, we don't have to have an operational configuration to say, oh, now catch up from this one over here, right? So that leads to a pretty sort of easy to operate model.
So actually, I have a use case that currently could benefit from this. We have 100 nodes, and I've run into the same I/O latency issues that you described in the first couple of slides. And so we use a local cache, a Google Guava. But this appears to be more elegant because you can, just Google Guava is local to the app server, to the node. But I do have a couple of questions. One is, you may have answered this just now, is how do you bootstrap a brand new data center? Like you have no nodes that are that have the updated transaction logs. And the second question is related, when the catch-up occurs, does the application have to handle the, you don't want customer requests necessarily to hit that app server while catch-up occurs, right?
Yep.
So how should
so there's a couple of things here. So all right, so that's a number of questions. So so the first one is, how do you bootstrap a new data center, for example? And so you have operational flexibility here, right? So one option is you actually spin up one node in the new data center, and you say, go catch up from that one over here, but you don't send any customer traffic over here yet, right? And the catch-up protocol will happily catch that guy up and bootstrap it there. Then you can stand up other ones that catch up from the original guy, right? And so you can do it that. The other way you can do it is you can just grab a tarball of those, transaction log segments, SCP, FTP, whatever you want to do, over to the other data center, put in all the nodes and just bootstrap them that way, right? And so, it's kind of whatever is most convenient for you. And then once you're up, you can start sending traffic. So there was a related question though about during the catch-up period, what do I want to do, right? So there's a couple of things here, right? Which is Sirius has one of the other things that's in the Sirius interface is there's a flag you can read which says, are you done bootstrapping off the replay log? Right, so what you can do is you can tie your application health check, for example, to that, wait for the replay to finish, and then get in. In most of the cases that you know about, right, which is like deployments where you're down for a short period of time, basically what it boils down to is you have to look at how tolerant are you of the eventual consistency, right? And so for a lot of our use cases, what we found is like it's fine to be out of the loop for 5 minutes. Because you'll catch back up, and actually because the updates are such a small percentage of the overall reference data set, we can tolerate a lot of propagation delay. Like it's just fine. Like it's okay. If you want to, you can also. I believe there are metrics that tell you what the most recently processed sequence number are, and so you can actually use that to compare to find out how far behind you are on various things. Did I answer all of your several questions? Okay, cool. I think. Okay, same question. Excellent. Replicated answers.
So are you saying that you have some other way to bootstrap this with the reference data set that's not the transaction log?
No.
Oh,
sorry. So yes, we do, but they're external to Sirius, right? So typically what we do is we actually have a separate system that sits in between the system of record for the reference data set and then the cluster that we're publishing into, right? So it actually looks for updates and then is responsible for pushing them in. And those things we can trigger bulk reloads on those things. So if we're actually bootstrapping the cluster for the first time, we can say, hey, just like go suck everything down and jam it in as updates. And we occasionally do that because it's like, oh, we had to fix a column in sort of the original data source, right? And so we want to get all those updates sort of pushed through. So we can trigger that, but again, those just look like regular updates from Sirius's point of view.
But in that case, then update speed is important in the bootstrap case.
It can be, right? And so that's one of the places to look at the right throughput. As I said, we got to the point where it worked well enough for us. Some of our bulk loads do take hours to do, but in a lot of those cases, that's been okay. We haven't needed it to go faster than that yet. Now, of course, like being able to do that in minutes rather than hours, like everybody would like that, right? But we're all busy, so we haven't gotten around to that yet.
So my question is about the number of keys that you can actually fit in your in-memory data structure, because reference data is good at 300, 400,000, but I have an application where I need 100 million keys. Mm-hmm. So is it something depends on me as an implementer of Sirius interface that I have to take care of the data structures like B trees and whatnot? Or do you have any plans to extend the size of keys you can actually support?
So Sirius doesn't care how many keys you have, right? That's the whole point is I wouldn't say you have to be in charge of your data structures. I would say you get to be in charge of your data structures, right? That was the point we're looking at here. But we definitely have tens of millions of keys running in production. 40 million, right? So within, but again, it's up to you to, you got to have enough heap space in your application. I've been told 60. All right, so there you go. So 60 million records and keys. Okay, another question over here.
I'm curious about the ordering of your updates.
Mm-hmm.
It looked like the API didn't, you're not imposing an ordering from your, from your updating service.
Yep.
Does Paxos take care of that for you somehow?
So it doesn't, right? So again, I would say this guarantees eventual consistency, but sort of not really strong consistency or transactional consistency. So in our cases, and in particular, right, the idea is that it's a key value interface, right? And as we saw in the log compaction, to some degree, ordering isn't that important as long as you've got sort of a later update here. Paxos just guarantees that you get a consistent ordering to it, meaning the updates are applied in some order on all the nodes. But the external publishing system, if it cares about the orderings of updates, right? The idea is that if I care about the ordering there, then the publisher can put one in, wait till I get an acknowledgement, and then put the next one in, right? And then that's a way to guarantee some of the ordering. Was that your question?
I think you just answered it. What I was thinking about was the values, they're arbitrary binary data, but what if they relate to each other somehow in a way that's opaque to you?
Yeah.
That could get into some real subtle semantics. However, as long as you've defined those, the semantics so that they're, any consistent ordering is acceptable, I think they're covered. But
yeah, that's right. Right. So you know, we try to be pretty clear about what we do and don't guarantee. So, for example, there's no referential integrity between keys, right? So you can, and we in fact do. Like the data structures that we have are actually heavily interlinked with one another, right? So, so a key that comes in for, say, a movie might refer to like a trailer of that, you know, or vice versa, right? And what comes in for like the movie or the trailer is just the ID of the other thing, right? So to some degree, like there's no you know, foreign key constraints that are in here. Like your application has to handle those if you want them. In a lot of our cases, we found that we can actually deal with that relatively well. But you do have to be, you know, to your point, you have to be aware that, you know, that's a thing, right? The other thing that Sirius doesn't do on the, or it can do, right, on the read side, right, when I'm accessing the data structures directly, like I'm in charge of handling concurrency on that path, if I want to take that path, right? And so we typically use concurrent data structures, you know, when we do that. If you want to, you can actually ask Sirius to enqueue a get. Now what that does is it doesn't do any Paxos stuff, right? All it does is it inserts that GET request somewhere in the serial list of updates that are being applied, right? So it schedules it sort of as soon as possible. And so if you want to, you can have Sirius say, you can do a GET where you know no other updates are going on at that point, right? If you want to. Now, we typically don't do that because you know, for a lot of the updates that we do, like we don't need that kind of locking, and we don't really want to have a serial kind of access there. So we tend not to use that, although that was sort of there from the early interface.
So this question about the iterable data sets, if I put it in Sirius where you have a load balancer, so I don't know where the request will go to, but what if the data structure needs to be a continuous iterable array list, let's say? So how do you predict which data set is received or sent back to the client?
Yeah, so remember, Sirius is going to replicate the full data set to all of the nodes, right? So the data set is not partitioned across the nodes. So the idea is that you don't care which one it goes to because all of the data is at whatever node you go to.
So my question was about the update. So let's say 10 of my nodes or 5 nodes did not receive the update yet. Yep. So the next request when a user clicks on show me the next 10 credit card transactions comes in. So it might go to the 5 nodes which have not been updated yet. So
yeah, so again, you have to be in a position where you're okay with eventual consistency, right? You know, so again, Sirius does not provide strong consistency on the reads. What you do get is that you won't get sort of like, oh, when I went to this server, I saw, you know, updates 3, 5, 8, and 9. Right, because Sirius will guarantee that you got them in order. Like I may go there and it may look like, you know, I may go to this node and it looks like, oh, I can see transactions 1 through 5. I go to this other node, oh, I can see transactions, you know, 1 through 8, because that's just where they are relative in processing the update stream. But again, you know, if you care about that strong consistency, then this is not the right tool, right? You know, this is about you know, external reference data sets where you're okay with some degree of latency propagation. So don't use it for that. All right. If anyone has any other questions, I'll be out by the Comcast table right outside.